So the corresponding synthesis filter for each element in the filter bank can be viewed as uh, like this. Okay, so let me just first give you the, sketch the input. So we have input y0 m, y1 m, and yn minus 1 m. Okay, so then we are just passing it through a upsampler. Okay, upsampler by a factor of d. Then these will be passed through a filter g0 n, g1 n, and this will be passed to a filter. Sorry, this is all our g0 actually, g0 n. Okay, so then output of this filter will be multiplied with a complex exponential of j omega naught n. This is also multiplied. Here the multiplication factor in this case will be e power j omega 1 n, and similarly the last channel, this is also multiplied by e power j omega n minus 1 n. So the output of these multipliers, okay, will be added, producing an output bn. Okay. So one thing you can see from here, the output at this upsampler, and before that let me tell you, we have assumed that I is equal to d. Okay. So the output at this node will be y naught m by I for m is equal to 0 plus minus I plus minus 2I and so on, and it is 0 otherwise. Okay. So at this node we'll be getting this. Similarly at this node we'll be getting y1 m by I for m is equal to 0 plus minus I and so on, and it is 0 otherwise. So then the output of this filter will be nothing. Basically, whatever you are getting at the input node of this filter, it will get convolved with the impulse response of the filter, and so we'll be getting. Let me change the color. So we'll be getting at this node. At this node, we'll be getting summation over m y naught m g naught n minus m I. Okay. So similarly at this node you will be getting summation over m by 1m g naught n minus mi. Okay, and here then they are just getting multiplied with the complex exponential of j omega naught n, and so on. The lastly it is exponential of j omega n minus 1 n. So what is this omega k? Omega k, as I told you earlier, omega k is nothing, it is equal to 2 pi k by capital N. Okay. So this part, basically what we are doing here in this part, we are just doing to the input sequence, or the input sequences are upsampled by a factor of d. So let me write down: input sequences are upsampled by a factor of I, which is equal to d. And what we are doing in this part, basically what we are doing in these, so here we are just uh, these are the filters, and these filters are used to remove the images basically. Okay, this will filtered to remove images. You know that when we are doing upsampling, the spectrum will get compressed, and you will be getting a multiple images of the spectrum within the from minus pi to pi. So it will just remove those images. Okay, and then the these multipliers. Okay, let me change the color. Uh, so these multipliers, basically it is doing a translation in frequency. Okay, translation in frequency. Okay, um, and that is obtained by uh, multiplying by the complex exponential. Okay, then finally the resulting frequency translations at all these channels will get summed up. So I think I should move to the next slide for the mathematics. Finally, I will be writing the mathematical expression for this output Vn, and I will be just writing a mathematical equation because I don't have space on this slide. So therefore, you can just while writing those equations on your notebook, you can just keep this diagram in front of your eyes. So let me just, so the Vn will be equal to 1 by n summation k from 0 to capital N minus 1 exponential of j 2 pi n k by capital N. Then there will be a summation ykm g naught n minus mi, and the summation is over n. So you know that what we at the output of the G naught filter we were getting, let me change the color. So at the output of the G naught filter we are getting this output, then that is getting multiplied with the complex exponential, then the output of all those n number of channels are getting summed up, so therefore summation. And here we have introduced a scaling factor 1 by n. Okay, so now this can also be written as we will interchange, we will do some term arrangement, and we can interchange the two summations. Since this is a linear operator, summation is a linear operator, so we can interchange it like this. Summation ykm exponential of j 2 pi kn by capital N. Okay, so the terms have been rearranged. Now what I will do, I'll just bring this 1 by n over here. Okay, so what I can just do here, I can just remove it from here, and I can just keep it in this bracket. This is a scalar, so then finally this will be equal to summation g naught n minus mi, and this is ynm. Okay, and this summation is over n. So what is this ynm? So if you look at this formula, which is hold a minute. If you look at this formula inside the square braces, so what this indicates basically, this is, I'm saying this is equal to this y and m. So what does it mean basically? So this represents basically the samples of the inverse DFT sequence of ykm. Let me write down ynm YNM, or the sequence of YNM represent samples of the inverse DFT sequence corresponding to the sequence YKM. So you can see the relation uh, between this and this basically. So from here you can easily observe this. This is nothing. This is the inverse DFT formula. So therefore we are testing this. So the finally the output is nothing basically summation over m g naught n minus mi y mn ynn. This is nothing. This is the inverse uh, DFT of the sequence ykn. Okay, and the sequence g naught n, since I'm using a curly braces, it means it's a sequence. So it means I'm just talking about the sequence. So G naught n sequence is the impulse response of the interpolation filter. And I is equal to D. Okay, so G naught is the impulse response of the interpolation filter, and the relation between the output xkn of the analysis filter bank and the input ykm is given over here. Okay, so let me move to an alternate realization of the analysis and synthesis filter bank. Let me move to the next slide for that. Okay, alternate realization of the analysis and synthesis filter banks. Okay, so let me sketch it for you. We have H naught n, H1n, H of n minus 1n, X n is the input. So we know that after this filter, after this filtering, we were doing a downsampling by D, then passing it, or multiplication with the complex exponential of minus j omega naught m d. So if you recall the uniform DFT filter bank which we have discussed earlier, if you relate this figure with the previous one, you can easily distinguish between the two. Basically, in that image or in that figure, first we were doing a multiplication with a complex exponential, then passing it through a common filter, basically H naught, H naught, H naught for each stage. Then we were doing a downsampling. Here, for the scenario is different. This is just an alternate representation of the or realization of the filter bank. So we will be getting minus j omega n minus 1 md. Okay, so these are the output, and these are x naught m, x1 m, x of n minus 1. Okay. So you can just compare it with the previous uh, analysis filter bank, where we have used, first we have done the multiplication with the complex exponential, then we are passing it through a common filter. For each channel we have used h naught, and then we were doing a downsampling and we were getting the same thing. However, this is just another way. Now let me just again give you an alternate realization for a synthesis band, synthesis filter bank. Uh, Earlier you have seen that basically in the previous slide you have seen that for synthesis filter bank, what we have done, we have just first done an upsampling by a factor of d or I, then passing it through a filter with having impulse response g naught n, which was removing images. Then we were doing a multiplication with the complex exponential. However, the here in this case the process will be different. Let me first sketch that. Okay. Then what we'll be doing, then here we'll be doing upsampling by d, then passing it through filter. This one is g naught n, and the second one is g1n, and so on, and the last one is gn minus 1 n. Okay, then we'll just, it all get summed up. So this will be your vn. Okay, and what is g naught n, g1n, and gn minus 1 n? Basically these are nothing, these are the band pass interpolation filter. Okay. With or let me just write it complete, with impulse response gkn is equal to g naught n exponential of j 2 pi kn by n. It means the impulse response of g1k is the shifted version of the impulse, or it's in frequency domain. Basically the spectrum of g1n and is shifted when you compare it with the spectrum of g naught n. So it's clear with this, with the multiplication of the complex exponential, because this is equivalent to shifting in frequency domain. So this whole we have on this slide we have sketched the analysis filter bank and synthesis filter bank, and this is nothing, this is of alternate realization of uniform DFT filter bank. Okay, alternate realization of uniform DFT filter bank. So that's one thing. Let me move to the next slide. So the filters are realized as band pass filters with impulse response HKN is equal to H naught n exponential of J 2 pi Kn divided by capital N, and where K is 0, 1 till capital N minus 1. Okay. So the modulation of the modulation by the complex exponential, basically we are doing a modulation with this complex exponential, that is multiplying by this complex exponential, allows us to shift the spectrum of the signal uh, from some frequency, say for this case omega k is equal to 2 pi kn by n, to omega naught is equal to 0. Let me just write down this fully. The modulation by the complex exponential is, that is, multiplication by exponential of minus j 2 pi k by capital N, okay, allow us to shift the spectrum from omega k is equal to 2 pi k by capital N to omega naught is equal to 0. Okay. So the analysis filter bank output, that is xkm, the analysis filter bank output, that is xkm, will be equal to summation n x of n h naught md minus n exponential of j 2 pi k md minus n, and then this is exponential of minus j 2 pi k m d by capital N. Okay. So on the previous slide I showed you an alternate analysis filter bank, and the output of that is nothing, is this actually, that's mathematical explanation for that. Similarly for the synthesis, this slide is about the analysis, alternate uh, realization of analysis with the bank. On the next slide, I will be showing the synthesis filter bank mathematics. We have seen that in synthesis structure, gkn is equal to g naught n exponential of j 2 pi k n divided by capital N. Okay. So what is this basically? What is this? This is nothing. This is the impulse response of prototype filter, and other filters have been derived using these prototype filters by just multiplying with the complex exponential, or let me just write down for one. G1k is the thing that is equal to g naught n exponential of j 2 pi k by, so k is 1 in this case, so it is n by. Okay, so just doing a multiplication with the complex exponential, so the spectrum of this is nothing, it's a shifted version of this one. This thing we have seen in the beginning also. So finally the output of the synthesis filter, or the alternate realization of the synthesis filter, that Vn will be equal to, again this is a scaling factor 1 by n, and summation k is from 0 to capital N minus n. We have this many number of channels in that filter bank, so therefore n summations. Then within this we'll be having a summation uh, ykm exponential of j 2 pi kmi capital N gk n minus mi, and this is over m. Okay, so and here you assume that I is equal to d always. Yeah. So so that's the thing. One more thing I want to say over here, while implementation of a digital filter bank, computational efficiency can be achieved by use of polyphase filters for decimation and interpolation basically. Okay, so basically uh, we have already discussed the polyphase filter structure. So if you use those polyphase filters, so obvious you can achieve you can improve the computational efficiency in that case. Okay, so that's one thing, and let's move to the next lecture. So let's discuss the polyphase structure of uniform filter banks. Okay, as I told you that while implementing a digital filter banks, the computational efficiency can be achieved by use of polyphase structure of when you're using a polyphase filters. So let's continue.